Olá a todos novamente. Vamos agora iniciar a sessão de palestras, a primeira com a Sofia Celi. Esta sessão será em inglês, uma vez que a Sofia é do Equador, por isso não fala português. Hi Sofia, how are you?
I'm good.
So, as I was saying, Sofia is from Quito, Ecuador, a cryptography researcher and implementer at Cloudflare. She also currently leads the design and development of version 4 of the off-the-record messaging protocol. She is very involved in helping and in gender-based violence that uses digital tools in the Global South. She is interested in programming languages, compilers, usables, security and privacy by design, post-quantum cryptography, and real-world applications of cryptography. In this talk, we will look at certain topics of cryptography. Where did they start and what they are now? We will also look at them from the theory perspective and how they evolved into real-world implementations. Sophia, nice to meet you, and the stage is yours.
Thank you so much. I'm going to share my screen. Give me a second. Okay, let's see if I can share screen.
You have to click on present to all this. It's the third button. Okay.
Okay, is it working? Is it?
Yes,
okay.
We're watching.
Thank you so much. Okay, so thank you very much for inviting me. I hope that everything has been going really nice in this event. So as it was said, my name is Sofia Celi, and today I'm going to give a little bit of an overview of what cryptography is, from the theory and also to the application. So if you're interested more from a theory perspective, you have some insight in this talk. And if you're interested more from a software implementation or hardware implementation perspective, you also have some insights that you can get from this talk. So who I am, as I already said, I'm a researcher and implementer of cryptography at Cloudflare, which is CDN provider for many services. And I'm also very interested in the research that I do around post-quantum algorithms, formal verification, and many other things. If you want to learn more about what I do, the kind of work that I do, here's my website on the slide. So let's start right in. So basically, what is this talk going to be about? Like I created here on the slide a little bit of an agenda. So what we're going to be looking at, it is what is cryptography? What are some of the cryptography properties that we care nowadays in modern cryptography? Then what are the applications of this modern cryptography? And lastly, at the end, I will talk a little bit about the future of cryptography, what new research ideas are there, but what new challenges are there for cryptography. So maybe if you're interested, maybe that's something that you can explore. So let's start with the first one. So what is cryptography? As this is a talk about an introduction to cryptography, first we need to define exactly what is cryptography. Cryptography can be defined as the science that studies the techniques to make secure digital communication in the face of adversaries. Here, as you see, this statement has a grammar mistake. Make secure is not usually how you write it in English, but I put it that way in order to better explain the definition. So let's start breaking this definition into small bites, into smaller sizes to understand. So as I said, this is basically a science that it studies, but it doesn't study just as an abstract level or on a completely isolated level, but rather it's a study that goes from the theory perspective to even the actual practice perspective, to even the implementation of software, for example, perspective. It studies not something in the vacuum, but rather it studies specific techniques. And in this case, the techniques that we use in cryptography most of the times are algorithms and protocols that we implement into the real world, into real networks. And the aim of this study is to study these techniques that try to make digital communication secure. What does this mean to make something secure? We will look in the next slide. But just to give you a little bit of a flavor, prior to make secure in this case is to make something, to use encryption to make it confidential, but it's not only that. It also means, for example, preserving several privacy properties that sometimes data should have. And of course, this is the idea of making secure digital communications because we're talking to networks that work into this digital world, meaning in the internet. Cryptography in the ancient times was mostly the purpose of it was mostly to secure communication of the real world, for example, communications that happen at war or communication from a political perspective. But nowadays, it's mostly focused on providing security for communication that happens over digital means. And it's very interesting to also think about one thing thinks about cryptography is that this is a study of make communication secure, because these communications are always threatened by adversaries. Adversary can look at the network, can look at protocols, can look at the data and try to decrypt it and try to guess what is the contents of it. So it's always to make this communication secure in the face of some certain kind of threats, and in this case, the threat is the adversary. So let's just to give you a little bit of a historical overview of what is cryptography. Let's start with the past. So in the past, what was cryptography? As I already told you about, cryptography was mainly this study to make communication secure that happened specifically at war, or for example, at political communications. So let's say, for example, one of the most famous examples is the case of the Enigma machine. So in the case of the Enigma machine was this machine that was used in order to encrypt traffic, to encrypt certain messages and those messages were related to for example, the troops' position during Germany in World War II. And in that time, certain other parties, mainly Great Britain, was interested in decrypting this communication so they could actually know what the positions of the troop or certain other communications from the Germans at the time was. So they tried to decrypt those communications, and it's actually one of the most famous work of cryptanalysis, because these cryptographers are Bletchley Park. Basically, what they did was that indeed they managed to decrypt the communication, to decrypt the mechanism that was used by the Germans during war. And this is one of the greatest work of Alan Turing that he invested a lot of time doing. But as I said, it was just to give you an overview that in the past, cryptography was basically the science that was used to break communications in a political manner, but it was not really used in everyday. What we have now in modern cryptography is that it's not only used for encryption, and it's not only used for military or political data, but it's rather used in everyday transactions, in everyday communications that we use nowadays. Mainly when we open our browser on any kind of devices, we are going to be using cryptography in some flavor. Now, what is also the important thing to say about cryptography as a science? That the cryptography as a science is a science of probability, because any algorithm or any protocol that you put out there in cryptography can be broken with enough computational power and with enough time. But most of the times, the algorithms that we put of cryptography out there cannot be with this probability broken, because it will take an adversary, like for example, 1,000 years and like 500 machines running at the same time in order to break this algorithm, because the underlying mathematical construction in which this algorithm is based is too difficult to be broken by modern computers nowadays. So cryptography is not a perfect science. It's not a science that will never fail, but it's just a science of probabilities, meaning that you put an algorithm out there that can be decrypted, but it will take a lot of time for an attacker and a lot of resources for an attacker to decrypt it, and therefore is infeasible for an attacker to actually launch that attack. So that's basically. So what is cryptography based? In order to maintain this infeasibility of the attacker to be able to break the algorithm, this is basically the cryptography is based on computational hardness assumptions. So how hard it is to break. And if it's really hard to break an algorithm, then it's an algorithm that can be suitable for the real world. Now, let's start digging a little bit more about actually in cryptography in practice really looks like. And for this, we first have to model communication. So let's just do a recap on communication. What is communication? Basically, communication is this action that happens between actual participants peer, or sometimes you read them be mentioned as with other words, but mainly you will read them be mentioned as actor participants appear. It's basically this act between these participants who wants to send certain kind of messages and associated data of these messages in the form of metadata. And they want to send this data through an insecure and volatile channel. In this case, for example, they want to send it through the internet. They want to send it through a network, which is an insecure by default channel. And what they do in order to achieve this communication is that they are going to be sharing between each other a shared code. For example, they are going to be using bytes, or they are going to be using ASCII representation. So that's the shared code that they use in order to communicate. Why is this important for cryptography to actually model the communication model? Because if we're going to be talking about the different properties that cryptography can actually provide, then those are related to the model of communication in which you're putting this property in. One of the most famous properties that you will have in nowadays modern cryptography is these three ones that I have listed here, which is the property of confidentiality, authentication, and integrity. What does confidentiality mean? Confidentiality means what we often associate with cryptography, meaning that anybody but the recipient of a communication, the participant you're talking to, should be able to read the data, meaning that if someone, for example, gets your data, they will not be able to read it. They can get it, but they will not be able to read it, to know the contents of the data. Only the intended recipient, only with whom you're actually going to communicate, is the only one who should be able to read this data. The second property is the property of authentication, which basically means that you're assured that you're talking with whom you are supposed to be talking. So, for example, let's say that you are communicating as Alice to Bob. You are assured that indeed you are communicating to Bob and not to someone who's pretending to be Bob, and not, for example, Charlie, who's pretending to be Bob. And the last property is the property of integrity, which basically means that yes, the data that you're sending should be confidential. No one else should be able to read it, but it also should preserve integrity, meaning that someone in transit could not be changing the data. So let's say again that you're Alice and you're communicating with Bob, and you're sending to Alice a hello, a message that just basically says hello. And then Charlie captures this message and tries to change this message to, for example, to say bye. So that should not be possible with certain kind of cryptographic algorithms, because they preserve that even if an adversary cannot read the data, they should also not be able to modify this data to say something different. So now that we know actually those properties, let's look in a real world example of what they actually look like in an actual protocol that we use nowadays. And the protocols that I've chosen is this protocol that is called TLS. So what does TLS stand for? It stands for the Transport Layer Security, and it's basically a protocol that gets put on top of TCP or UDP. And basically what it tries is that it tries to make secure those connections. How usually TLS work is that TLS have two phases, one handshake phase and one record phase. Currently, the current version of TLS is the version 1.3, and it was in the making for about 5 years or more. And it's basically the version that we should be always upgrading to. So how does TLS work though? As I say, it is divided into phases. The first phase is the one that we're actually interested in these slides and the subsequent slides, because it's the one where cryptography actually happens. TLS basically happens in that first the client will want to establish a connection with the server. Basically, a client, a browser will be saying to a server, hey server, please give me this website that my user wants to see. And the client opens a TLS handshake. What does he do? The first, the client sends a message that is called a client hello, where they say like, hey, I am this client and I need this website. And it also sends a message that contains a thing that is called a key share. What's a key share is basically certain cryptographic algorithms that they say, hey, I want server to please give me this website, and these are all of the cryptographic algorithms that I support. So if you support any of them, maybe then we can encrypt that connection. So when you return to me the actual website, that website is indeed returned in an encrypted mode. So that's what their client sends to the server. It sends the client hello and the key shares. The server receives this client hello, process it, and then receives the client the key shares. And then from all of that list of cryptographic algorithms that the client just sent, the server decides, yes, I support this specific key share. Therefore, let's encrypt the connection with this specific cryptographic algorithm. And what the server does is by certain algorithm that we will look in the next slide, the server manages to decrypt the first shared key that is going to be used to encrypt all of subsequent connections. The server at the same time sends a thing that is called a certificate. A certificate is just an attestation, a validation that says, yes, I'm the server who you are supposed to be communicating with. And therefore, with that, the TLS handshake preserves the authenticity, because the server is actually providing a proof of their identity, a proof of authentication. The server sends all of those messages. It sends the chosen parameters. It sends the first key in order to encrypt the subsequent flows of the communication. It sends the proofs of authentication. The client receives all of this and say like, okay, I have verified your identity. Seems that like I'm really talking to the correct server. Let me derive these keys, and the subsequent flows of communication are going to be encrypted, meaning that anything the client and the server sends at that point are going to be encrypted. So the website that the server returns to the client is actually going to be encrypted. So all of that is very magical. So how that's happening much more zoomed in detail. So for encrypting the actual part of the TLS handshake, you're going to be having two functions, an encrypt function and an encrypt function. An encrypt function is basically the one that are going to be encrypting the data, and it basically takes the message that you want to encrypt and also the key that you're going to be used in order to encrypt that message. And it returns a ciphertext. And the decrypt function is just the counterpart of this encrypt function. Basically, a decrypt function takes the ciphertext and it gets the key, and it returns the same message that was encrypted. And the examples, for example, of these kind of algorithms are AES, are Chachapoly, and many others that exist out there. Yeah, so one of the things that you can start thinking about this now is like, okay, that looks really easy from an encrypt and decrypt position, but how is this key generated? Like, I know what the message is to this function because the message is basically the hello that I want to send to Alice, for example. What is this key? How does this key get generated? So the first thing, how does this key get generated is basically a random amount of bytes that you generate, and you use that as a key. And then the next question that you can have, okay, now that is good. I have generated my key. How do I distribute this key? Because Alice and Bob should have had the same key. But even if I'm using an insecure channel, how am I going to transmit this key in this insecure channel without an attacker capturing the key and being able to decrypt any of the other subsequent traffic that I'm going to be sending? How do I distribute this? There are many ways. There's a way in which, for example, you can take the key and actually put it in a USB stick and send that to your partner or to your participant who you want to talk to, and you give them the USB key, and then you have a key that you're going to be using forever. Or another thing that you can use is a protocol that is called Diffie-Hellman. And this is a cryptographic construction whose basis is a mathematical construction. The basis of this construction is basically the problem of exponentiation. How does it actually work? Alice and Bob, in this case, are going to have a common paint. In this case, they're going to have as common the color yellow. To this, they add the color red. Alice adds the color red, and therefore then they have the color orange. And Bob adds the color green, and therefore that comes to blue, because yellow and green is blue. The red and the green that Alice and Bob just chosen is their secret color, so that's their secret key. But the generated orange and blue are the public colors, and that they send to the other participant. Alice takes the orange and sends the orange to Bob, and Bob takes the blue and sends the blue to Alice. Once Alice has this blue, they mix with their secret color, which was red, and they get brown. And Bob, in turn, takes the orange that was sent and mix it with the green, their secret colors, and get brown. And in this way, they have shared public colors, but they have not shared the secret colors, and they have arrived to the same color. So in this way, what we see is that they managed to exchange keys, exchange colors, without having to disclose what their secret key was. In this case, what you see is that the two participants managed to actually get the correct keys without having to disclose any of their secret colors. In this case, and in this example, I have been using colors, but you have to think that instead of colors, what you are going to be using is that you are going to be using numbers, and you're going to be using the problem of exponentiation to it. So for example, Alice and Bob, for example, choosing a common number, which is going to be the number 2. And to this 2, Alice says, my secret number is going to be 2, and Bob said, my secret number is going to be 3. 2 to the 2 is 4, and 2 to the 3 is 8. They sent 4, which is the public number. Alice sends that to Bob, and Bob sends the public number 8 to Alice. And therefore, when Alice receives the 8, they exponentiate it again to the secret color, which was 2, and they get 64. And Bob, in turn, receives the 4, exponentiates to the 3, and they get 64. And therefore, they have arrived to the same number without having to disclose the secret key. And that's basically the magic of Diffie-Hellman. As you see here, it's really easy to do this if you're thinking about the small numbers or you're thinking about colors, but in cryptography, we use very big, large prime numbers that are really difficult for an attacker to guess. And this is the hardness assumption because it is difficult to guess these numbers. Not impossible, but it's difficult to guess for an attacker. That's the confidentiality part. In practice, it's much more complicated because you can have key leakage because sometimes you're using programming languages that are insecure. You did not properly store your keys or you did not properly rotated your keys. Your memory is leaking again the keys. So in practice, it's a little bit more difficult. And that's where you actually have to take other more forms of security in order to protect these keys. Now, that was for the confidentiality part of TLS 1.3. What about authentication? What do we use to actually provide proof of who we are? What we use is a thing that is called a digital signature. And you will have seen that, for example, when you are visiting certain websites, they say that they have a certificate. What is this certificate? This certificate is basically an attestation that says to the whole world that you are the owner of certain public key, and therefore you are who you're claiming to be. So anytime that a client contacts that server and that server publicly has stated that they are who they are and has a certificate of them, then you are actually providing proof of your identity. And the third thing that TLS Handshake provides is this notion of integrity. That is just basically that you take all of the messages that were previously sent, you hash them with a hash algorithm that we have in cryptography. And if you arrive to the same hash text, then you are sure that no one modified any of those messages in transcripts. So it's basically using a specific algorithm to be assured that no one indeed modified any of the messages that you sent. And that's it. So basically, that's how the TLS 1.3 handshake works. And it provides confidentiality by using Diffie-Hellman to derive a key. Then it uses an encryption algorithm to encrypt certain parts, all of the subsequent messages that you're going to be sending. Then it also uses a certificate to provide proof of authentication of the server and of the client. And it uses hashing algorithms to preserve the integrity of the whole transcript. So that's something, for example, that we use in modern day cryptography, and it's used on every connection that you will potentially be making when you visit a website. But that is not enough. New threats are coming, new attackers are coming. So what's the future in cryptography? One of the three concerns that I see right now in cryptography is these trees that are listed here: post-quantum cryptography, privacy-related things, and implementation and deployment concern. On the privacy part, as you have seen here in this talk, I have only talked about security and a little bit about authentication and integrity. But it's also worth noting that, for example, making metadata secure or making your identity completely hidden, arriving to anonymity, for example, is something that is also something that cryptography can also help you with. And on the first point, which is the third point, sorry, which is implementation and deployment consent, we already talked a little bit about that in the sense of what about if you really use this beautiful protocol, which is Diffie-Hellman, but somehow you put your key in an insecure place, you put it in a part of your memory that is accessible by attackers, then that's an implementation consent, because from the theory, Diffie-Hellman is all perfect, but if in the implementation you leaked your key or you published it on a website or you publish it somewhere, then an attacker can get it and can still break your algorithm. Not because in theory it has failed, but because in practice it has failed. In cryptography, we also have to think about safe programming languages and actually thinking about programming languages that preserve the memory and the memory allocation. So memory safe languages, thread safe languages, type safe languages, and languages that provide constant timeness. So an attacker will not be able to guess by doing timing attacks or by trying to look at the memory and trying to extract keys from it. So we prevent attacks in the implementation of cryptography itself. And that's still a big concern. This is not a solved problem. So if you're thinking about something you would like to work on, this is actually a big area that still needs a lot of work. And the last threat that we have right now in cryptography is the threat of quantum computers. So in the computers that we use nowadays, we follow a classical approach of the computational theory, in which one thing is one thing or the other, meaning it's just one an on or an off, a 0 or a 1. But then there's also this new computational model that started in 1980s that tried to emulate quantum physics. And the reason why this model exists is because they wanted to be able to simulate quantum mechanics experiments. And this is nowadays called quantum computers. The problem is that quantum computers are able to break almost all of modern cryptography that we use nowadays. They are able, for example, to solve in a really easy amount of time the factorization problems. So right now, what we're doing, a lot of researchers, we are doing this, is that we are changing now these algorithms to certain other mathematical constructions that are not broken by a quantum machine. And those alternatives are, for example, cryptographic constructions that are based on lattices or isogenies or hashes or codes, because that is safe even in the threat of a quantum computer. So basically, we're looking into that. And currently, NIST is running a competition to choose these new algorithms. But there's still a lot of open questions around them, if they're actually all of the security properties on these algorithms actually hold in the face of a quantum computer, what happens from an implementation perspective, how we're going to migrate all of modern cryptography to this new post-quantum cryptography. So this is still a big area of research. So if you're someone that is interested in cryptography, from the theory, there's many things that you can do, from algorithms or mathematics. From the implementation, there's many things you can do, either implementing algorithms or looking at how algorithms can be broken from an implementation perspective or from a hardware perspective. You can do analysis or cryptanalysis of algorithms. That's also a really nice area of cryptography. Or you can also do formal verification, which actually is using computer help in order to check the security property of your algorithm indeed holds or not. So all of those are avenues. Cryptography is a broad science, so you can choose from any of those topics. And with that, if there are any questions, I will take them now. And thank you very much.
Thank you, Sophia, very much. We will have now a short moment for Q&A. And while we wait for some more questions, go visit Sophia's website, sophiaselli.com. We will leave the link in the chat in case you forget it. The first question is the Diffie-Hellman still a widely used algorithm, or is there any more recent algorithms?
Yeah, that's a really nice question. So it's really used nowadays. Every day that you do a TLS connection, you're going to be using basically Diffie-Hellman. There's another flavor of it, which is elliptic curve Diffie-Hellman. So what you're usually using in Diffie-Hellman is that you're using really big prime numbers that you're going to be exponentiating with too. But you also can use another construction that is called elliptic curve cryptography. And that's basically that you choose a point in an elliptic curve, and that's going to be your public key. How you chose that point is you just basically took a generator and multiplied it by a scalar, and then you have your point. So that's a little bit a more fancy construction. So you either use the classic Diffie-Hellman with just numbers that you exponentiate, or you use elliptic curve Diffie-Hellman, in which you're going to be using points and scalars and using that representation for securing your connections. But yes, it is used nowadays. Something extra is that there's no post-quantum counterpart of Diffie-Hellman. So that's also something that we have to start thinking about, because there's no way to do a one-on-one changing of this algorithm in the post-quantum world.
Thank you, Sophia. So we have 3 more questions. What do you? I'm going to show you. What do you think about password managers and how do they assure security? Made by Andre Moreno.
Yes, yeah, that's an interesting question as well. So password security is very complicated because, as I said, usually when you generate a key, it has to be random, right? But passwords, for example, are not random. And sometimes we use passwords which are not random to encrypt certain parts of the communication. And therefore, it's really easy to broke because the key is not really that secure. So using a password for that is not the best. So that's why sometimes you have these recommendations of like generating random passwords or making your passwords look as random as possible because of that. So they are not great in general, the usage of any password from a security perspective and also from a usability perspective. Users don't really remember passwords. Users sometimes reuse passwords between different services, or if they're really, you generate password for users that are really random, then no one is going to remember that password. So it's a really challenging problem. For this, I know that exists certain password managers that can either generate the password for you and also correctly store that password. So in the case that you forgot it, you have a place where you can fetch it. Most of them are good. I, for example, use KeePass. I don't like a lot the ones that you use in the browser because sometimes the browser can also leak things. So it is better the ones that you install as an application in your computer itself. But in general, using password is something that the community has been discussing and debating a lot nowadays. For example, there are new proposals using WebAuthn or using something as opaque, which is almost passwordless. So we don't have to be relying in the security of passwords anymore, but rather we will be relying on all the mechanisms for it.
The next question is, are there rules to decide which secret colors numbers to use?
Yeah, so it's not as simple as just choosing any number. I just did it for simplicity. But they usually have to be prime numbers, and they have to be prime numbers of a specific group, because those are the ones that we know that a computer will have a hard time guessing them. So usually the base, remember that we had in the colors, we have this yellow, which was the shared color. Usually we use the 2 because that's so good enough. But for the number that you exponentiate to, that is going to be a random number, and then the generation of this base exponentiated to the random number should be a specific prime number that belongs to a specific group. So yes, there are specific rules. It goes into a lot of the details around the underlying mathematical principles of cryptography, but yes, it couldn't be like any number, and they also have to be really big. So because I don't know, a computer will be really easy for a computer to guess that if you give them 4, they're going to tell you, oh yeah, that's 2 to the 2 exponential. Like anybody can guess that. But if you give them like an X number that is gigantic, they will take a lot of time trying to guess how it came to be.
And for the last question, when can we expect to see new effective methods to counter quantum computing, which is breaking the current methods?
Yeah, so that's a good question also. So right now, currently, there's this NIST, which is the National Institute of Technology Standards of the United States, is currently running an ongoing competition to choose these new post-quantum algorithms. And the recent communication that they had, they say that they are going to be having, they are going to be announcing the actual finalists next year. So probably next year we will know which post-quantum algorithms we can use. But then there's a difference between when they actually announce to when they actually are standardized. That is going to be taking, again, an X amount of years. And then to actually implement it into the software and into the hardware is also going to take X amount. So even if they announce it next year, it's going to be taking 20 years or more in order to actually have it in real world connections. But the idea why we're doing this very early on, because right now there's not a quantum computer that is really efficient to be used. There's some experiments by IBM and by Google, but it's not quantum computers that can be used nowadays. Why then we're caring about post-quantum cryptography is because even if a quantum computer doesn't exist right now, an attacker can still record all of the traffic that you have sent. And then when a quantum computer comes 100 years in the future, they will take all of that past traffic that they recorded from you, and they will all be able to decrypt it at the same time, everything in the past. So that's why NIST and other people are very worried, because we need to make this transition as fast as possible, even if we don't have a quantum computer today.
Thank you, Sophia. That's all the questions. I would like to thank you so much for participating in this event, and for this really interesting talk. I will now switch to Portuguese so that talk to the people at home.
Yeah. Thank you very much.
Vamos agora passar para um pequeno intervalo. Voltamos às 4h30, por isso estejam desse lado.